The early 1950s was a defining period for Indian science. Scientists and administrators set about to lay the foundations of a blooming landscape of science with two goals: to fast-track the development of the state and to play an active role in the global endeavour of science. In 1952, C.V. Raman, one of the greatest Indian physicists, received a letter in this spirit from A.L. Mudliar, a renowned educationist who was the Vice-Chancellor of Madras University at the time. Mudliar intended to build a physics department in Madras University where world-class research would be conducted. Naturally, for such a Herculean task, Professor Raman was his first choice. Raman, who was busy with his own institute, wrote back suggesting a candidate as good as himself, yet much younger. A protege of Raman, he would build and head the department with expertise, drive and vision. His research would make the department a talking point throughout the global scientific community. He would lay the foundations of an entire field of research in India. And so in October 1952, Gopalasamudram Narayan Iyer Ramachandran arrived at Madras University as head of the department at only 30 years of age. His greatest contributions would be career-defining for any scientist. He discovered the molecular structure of collagen, outracing elite scientists who had previously sought to discover the structure of DNA. And his crown jewel, the Ramachandran Map, is a fundamental tool used by hundreds of thousands of biologists worldwide today.
You have to give G N Ramachandran great credit because Ramachandran actually created a first-rate environment.
He always felt, I think, that we should be as good as anybody else in the world.
You could be competing with the top-end international groups, but you should have the courage to do that.
The Ramachandran team did not complain that they don't have computers to do it, they don't have facilities. They just wanted to do it.
Somewhere around there is when he started developing some psychological problems. With all that he was managing, none of it stopped his work.
In Madras University in 1952, I chose X-ray diffraction and X-ray crystallography in particular as the main theme for the laboratory, and the applications to biomolecule is the main aspect of this field that is to be pursued rigorously. However, I did not know where to begin and on which molecules and biopolymers are the most profitable ones to study. The problem was resolved by the happy coincidence of visiting Professor J.D. Bernard to Madras during this time.
John Bernal was a British crystallographer and an important figure in the early development of structural biology. The problem of the structure of collagen was a hot one, and there was a race between top labs in Cambridge, Caltech and others to solve it.
When I put this question to him, he told me that he was not very happy with the various structures of collagen that had been proposed in the literature at the time, and that the problem was wide open.
But why were researchers who solved the structure of DNA after this protein? For one, the problem was considered to be tougher than DNA. And secondly, even among proteins, collagen holds an important place.
Collagen is a building block of all the cellular material.
If you take the total body of a human being or any mammal and take the water out, the most abundant protein is collagen.
The bone, the cartilage, the tendons, they're all made out of collagen. It's a highly talented molecule. It can bend, it can twist because it can adjust itself to the surrounding pressures. People have now realized the utility of collagen for several practical applications.
The autoimmune diseases of collagen which are non-killer, like arthritis. Burn injury is very common in this country. Ulcers. There is a disease, Cinematography imperfecta, with just replacement of one glycine by an alanine. The longest life people live is 12 years. Can the society afford not to understand the genetic diseases of collagen, enforced by structural biology of collagen, and live with it.
You have to give G N Ramachandran great credit because, when he went back from Cambridge to Madras University, he, had to basically start up things from scratch.
He was a very hands-on person, and he built his own X-ray crystallography machine and things like that.
I don't think we can divide Professor Jain's work as, this is theoretical, this is experimental, this is computational. He was somewhere along rolled up into one.
The laboratory at the Department of Physics, University of Madras, was well equipped.
He was going to be the only person in that department. Everybody else was a student. And of course, built up the staff slowly.
It was done in splendid isolation. It could be seen as an advantage also. He was not biased by the thinking process coming from the West. He probably enjoyed, among the disadvantages, an advantage of being able to be very, very original in his work.
So for him, everything was a picture, everything was a 3D image in his head. That to me was his major strength. He could visualize and he could come up with answers long before he had the maths to codify it and put it down in a paper. And then, of course, he'd drive his students mad trying to get it just right.
So I met Ramachandran once. It was not a warm, fuzzy meeting, but it was certainly an intellectually interesting meeting. And after we finished talking, he gave me an assignment. Here's what I want you to do, he said. And because of my great respect for his work, I didn't react in the usual way I would have to some stranger telling me what I must go back and do. In fact, I went back and did it. So,
helping Ramachandran to solve the structure of collagen was a bright postdoctoral researcher named Gopinath Kartha. So to start out, Ramachandran had to find a sample of collagen. Fortunately, right next to his department was the newly opened Central Leather Research Institute. Ramachandran went over to talk to their deputy director, Dr. Nayudamma.
Professor Nayudamma, as a leather technologist though, he realized that what Professor Ramachandran wanted is a pure sample of collagen. Then he said, why don't I go and collect kangaroo tail tendon? Nayudamma went to Australia for some meeting and collected a sample of a kangaroo tail tendon, put his coat pocket and brought it to this country and had his colleagues purified for him.
Even if one does get pure collagen, you need to place a hair width sized piece in front of the X-ray. A camera might take a second to click, but X-rays could take multiple days back then. The X-ray pattern is like a negative, except it's just a few dots. An X-ray crystallographer tries to develop this into a picture using complex physics and mathematics into human-sized models. At a time when solving the structure of 100 atom molecules was a considerable job, solving the structure of a 10,000 atom protein was monumental. Ramachandran and Kartha spent months trying to get a decent X-ray pattern. Once that was ready, they began to construct a model. The lack of modeling kits did not stop them, as they used ribs of coconut leaves, cardboard cutouts, and wax to build and visualize their structure. But if the previously proposed models were interpreted with similar X-ray patterns, how could Ramachandran and Kartha develop a better model?
Kartha and Ramachandran proposed a triple helical model for collagen. That's the first time that anybody said that the collagen is a triple helical coil structure.
It was novel in several ways. One is a single strand of protein winding around a left-handed man, and 3 such coils winding around each other in an opposite-handed manner.
We used to make fun of the triple researcher of collagen. He got the inspiration from the rope the women used to get water from the well. Once I asked him very gently, where was the inspiration from? And he says, the manners in which the celestial bodies move around each other, he saw a helical model. And that's what he said was his inspiration.
The breakthrough to the collagen problem coming from Madras University took the structural biology community by surprise.
Pretty amazing, really. They got to the right answer before anybody in the US or Europe did. And they were supposed to be the main centers.
Ramachandran and Kartha's model of collagen soon gained fame as the Madras triple helix. For Ramachandran, the victory was more than about solving a difficult problem. His incentives were deeply linked to his three gurus.
So he said that he had joined the electrical engineering department in IISc to do PhD. And then somehow Raman and he got in touch. Once he and Raman had started interacting, this is what my father says, he went to the head of the department of electrical engineering and said, Ramachandran is wasted in your department, I'm going to take him off your hands.
He spotted his talent right away. C. Raman had special regard for G N Ramachandran also.
It was under Raman that I think Ramachandran's talents and interests in optics and crystallography really grew.
When he went to Cambridge, what he found was biology was in the air, because they could see that they had a set of tools in physics and the tools could be applied to better understand biological systems. It was the biggest, the greatest group in the world at that time. So he also joined it.
During his second PhD in Cambridge, Ramachandran worked in Cavendish Lab, which was run by William Lawrence Bragg. He also got a chance to interact with a visiting professor from Caltech, Linus Pauling. Interacting with two of the greatest scientists of that time would deeply influence the young scholar. To understand their impact, we need to go further back to the beginning of structural biology. In 1912, William Lawrence Bragg, along with his father, William Henry Bragg, set the foundations of X-ray crystallography with their famous Bragg's law. They were awarded the Nobel Prize in Physics in 1915. Meanwhile, Linus Pauling was engrossed in understanding chemical bonds, the very forces that formed molecules. In 1931, he would propose the valence bond theory, which is a landmark in our understanding of chemical bonds. This period also saw the emerging importance of proteins and nucleic acids in biology. And so Pauling and Bragg joined the pioneering scientists who began to study biomolecular structures. They engaged in a friendly rivalry at the prospect of making history. The first race they embarked on was to describe the structure of the alpha helix, which shapes a vast number of proteins. Pauling and his team won this race in 1951. The next exciting race was for the structure of DNA. Members of Bragg's team at Cavendish Lab, James Watson and Francis Crick, would vindicate him in 1953. A couple of months later, J.D. Bernal informed him that the teams at Caltech and Cambridge, among others, were now chasing the structure of collagen. This was his opportunity to etch his name in history alongside leading scientists synonymous with early structural biology. Alongside his mentors who inspired him to pursue the study of biomolecular structures. But alas, his victory was short-lived.
Subsequently, there was a paper in Nature by Crick and Rich, which said almost right at the beginning of the paper that the Ramachandran and Kartha model is wrong.
When the paper came out, he was very upset. And the accusation is that some of the stereochemistry of the model was not okay.
So all atoms are slightly sticky, they're attractive to one another. But if they get too close so that their electron clouds overlap,
but they're not bonded to one another chemically, then they are very strongly repulsive.
You know, right from the time when the alpha helix and the beta structure for proteins were published by Linus Pauling, the assumption was they have to be the most stable possible structure.
Just based on optimizing hydrogen bonding, which was something that Ramachandran did, which was to recognize that you want to make the optimal number of hydrogen bonds, but at the same time, you can't bring atoms so close that they overlap with one another.
But they brought the three helices together a little closer than what probably was.
In a private letter to Ramachandran, Crick and Rich acknowledged that, quote, your type of structure was on the right lines and that the collagen problem has changed completely as a result of your work, unquote. The Ramachandran Kartha model was the first instance that collagen was proposed to be a coiled coil structure. This was a key feature of the structure that the other groups had not deciphered. However, within months, other groups also published coiled coil models for collagen.
There is a controversy about that paper because apparently the Nature sat on it for a long time and they gave access to that work to Rich and Crick, who were also working on collagen structure.
Coincidentally, Gopinath Kartha was in London at the time and his letters to Ramachandran shed some light on the matter. Ramachandran's paper was sent back for revision, and according to Kartha, the general idea seems to be that the publication of our paper was purposefully delayed by months for them to work up an idea after seeing the manuscript.
All they did was just a little bit rearrangement of these helices to get rid of these short distances. So with that they could make it a little looser structure. And they actually published that paper almost simultaneously with the Madras group paper. That kind of became more of the accepted structure.
Sitting in India, you have no power in all this. So you just have to swallow your anger and put a brave face and smile. By today's standards, that would have been extremely unethical. But at that time, they did such things.
In those days, communication was absolutely almost zero. So it's not like, you know, you're exchanging mails or picking up the phone and talking to people. Even your journals would take 3 months to come because they would come by sea mail and things like that. And it's again not a rigid structure. So what you see is sometimes what is the Ramachandran structure and you see sometimes what is the Rich and Crick structure. So it varies a little bit. I mean, the difference between the two structures is so little. But the basic idea about the triple helical coil structure was Professor Ramachandran's. There's no doubt about it.
During such tumultuous periods, Ramachandran had to rely on his constant pillar of support, his wife Rajalakshmi.
Somewhere around there is when he started developing some psychological problems. Manic depressive features were there. And that all fell on her shoulders. He was regularly going to a psychiatrist and maybe psychologist also and getting treated. A huge number of drugs. When he took these drugs, he said, my mind is not sharp. At that point in time, I think my mother was of the opinion that all the sharpness is enough, you've done good work, now just become calm. With all that he was managing, none of it stopped his work.
According to science philosopher Thomas Kuhn, when there are inconsistencies in normal science, scientists have to conduct extraordinary research to lead a scientific revolution. This is the way science progresses. Coincidentally, around the time Kuhn published this, a real example was unfolding. As Ramachandran obsessed over his discredited Madras triple helix, he decided to do the unthinkable. He decided to challenge the knowledge of molecular physics. And what followed was nothing short of revolutionary.
It was just his boldness. All of us who worked with him, I think that was one thing we picked up from him, that you should be able to question everything which is there and to explore new ideas and new problems. And if you think something is right, just go and do it and stick to it.
GNR was bent on proving that he was right. And in asking the question, I think Ramachandran and his colleagues came upon what I would call a profound organizing principle of protein structure.
Ramachandran, being Ramachandran, tried to come up with a systematic way of finding out whether there was steric clash.
Now that raises the following 2 points. Number one, how do you judge whether a structure is good or bad? Number two, how do we generate good models as a starting point?
So the assumption at that time is that they can come closest, which is equal to the sum of their van der Waals radii.
This is inherently wrong because van der Waals radii are derived from gaseous state.
When I started looking up the literature, there are at least 15% of the data had distances less than the sum of the van der Waals radii between two non-bonded atoms.
So definitely the Crick and Rich's assumption that non-bonded atoms cannot come closer than the sum of the van der Waals radii is clearly wrong. And then how do you get the actual, the shortest approach distances between atoms?
They started an experiment to look at the basics of protein structure. The millions of proteins found in nature are all made from the same 20 building blocks called amino acids. Each protein has a unique combination of amino acids which determines the structure and properties of the protein.
I think the major principle to understand here, and if I may illustrate it with the pens which are there in my pocket, if I have two atoms, there's only one parameter which I can measure, which is the distance between them. If I now have three atoms, I can now measure two bond lengths and one bond angle. But now when I have four atoms which are connected to one another, now you can see I have introduced the element of three-dimensionality. So I am now rotating about a torsion angle. This is what in the polypeptides we call the Ramachandran angle phi or psi. So when you deal with torsion angles, you're actually dealing with a three-dimensional parameter. And this is what makes them so powerful.
Two attached planes can also be turned around to create a three-dimensional coordinate for the peptide unit. This immediately suggested to me that you require two torsion angles to describe the conformations of the peptide unit.
So, for example, I have here a CPK model. So you could see that each atom is represented by something that is a solid sphere. Here's a carbon atom. It's the alpha carbon. And as you rotate around that bond, there are 2 degrees of freedom for each residue, phi and psi. And you rotate here, and then you rotate the chain around the next local angle.
They considered for a minimal system of peptide. Like the Crick and Rich, they also assumed the shortest approach between two non-bonded atoms is the sum of their van der Waals radii. You have the spatial arrangement of atoms. They checked all the non-bonded distances. If the sum of the van der Waals radii is shorter than the actual distance, then they considered the phi psi to be disallowed. Ramakrishnan, who was my thesis advisor, and he did his thesis with Ramachandran, and Ramachandran Map was his thesis work. He has to calculate the non-bonded distance between all pairs of non-bonded atoms and then check each one of them with the contact criteria. This he has to do for every single one of 360 into 360 combinations. And all that he had to do this work was a calculator of the present day PC size, which can do only 4 basic operations: addition, subtraction, multiplication and division. There is no memory location. You can't store the number. And it has no trigonometric functions. It's not a scientific calculator. So for trigonometric function, he has to use a book called as Clark's tables. So you can imagine him painstakingly punching the numbers in the calculator and then writing down the result in his notebook and then re-punching the numbers back into the calculator to do all these calculations. It is the fire in them that kept them going. And so Ramakrishnan told me that it took him from morning 9 to evening 6, 7, every single day, 1 full year, he didn't give up such a marathon exercise, numbers after numbers after numbers, to complete all these calculations. And interestingly, the result they have got is no psi value is allowed. That is an absurd result because proteins are existent, peptides are existent in living systems. They should have some psi value. If you do some work and then say that no psi value is allowed, then proteins and peptides cannot exist, and you and me cannot exist.
We decided to have a set of distances which are about 15% less than the sum of the radii.
They call it the contact criteria. So they call this as freely allowed or fully allowed contact distances, and then they call something as a partially allowed contact distances.
So Ramakrishnan did all the calculations again. Then the rest is history.
What's the great breakthrough in the Ramachandran plot? In biological science, there are not theories in the same sense that there are in physics. But then comes the Ramachandran plot.
There are a number of great features about it.
With early structures, you're seeing all the atoms, and it's a forest, it's a jungle. That's the beauty of the Ramachandran plot.
It reduces the three-dimensional complexity into a two-dimensional representation, which is more easily perceivable by the human mind. Roughly about 30% of the psi combinations are only theoretically possible, and remaining 70% is not possible.
So it is, as far as I know, the only theory in all of biological science
where if an experimental result, which is the crystal structure of a protein, is not in agreement with Ramachandran Map, which is theoretical work,
then either you've got it wrong or you found something really new.
If your experiment is in violation of the theory, you suspect the experiment, not the theory.
It was done to validate the collagen structure. Now, if you calculate the psi values of the collagen model as proposed by Kartha and Ramachandran, they fall beautifully within the allowed region.
Well, in my view, the Ramachandran map was slightly ahead of its time.
There were problems in the early days of crystallography where some very incorrect structures had been produced.
Then the plot became a very important restraint.
So when you solve your structure, one of the first things you do is see what the Ramachandran plot looks like.
I think it took some time for the average protein crystallographer to be willing to be subjected to, to these rules and things.
Initially it was thought as just a physics person's theoretical concept.
Like a very abstract piece of work, not particularly useful because you needed to have a huge computer before you could start using it.
But in mid-80s, I think the computer graphics began to be sufficiently advanced, sufficiently powerful, the resolution of the monitors, the speed of the graphics processing. A lot of manipulations and analysis and visualizations of protein structure implemented through computer graphics as opposed to in real life with physical models.
There was a very large expansion of protein structures.
That's when the Ramachandran plot really entered into the mainstream.
As the PDB developed in the 70s,
which has every single structure of protein anywhere around the world when they submit coordinates to that data bank.
They had requirements to check their maps before they were deposited in the PDB.
Probably if today we talk about bioinformatics as an area, perhaps he is the originator of bioinformatics in that sense through his so-called Ramachandran plot.
It's built into a lot of software and will continue to be built into software.
Today, several hundreds of thousands of protein structures have been determined, and every protein structure has to pass G N Ramachandran test.
The Ramachandran plot became central to my thinking and my life in structural biology.
And thus, the names of Ramachandran, Shashi Shekharan, and Ramakrishnan became known to every protein biologist across the world. Such was the caliber of G N Ramachandran. His own protein structure failed a test, so he created a test for every protein ever studied. It is remarkable that Ramachandran made foundational contributions from India in the 1950s and 60s. While researchers in established centres like Cambridge and Caltech would meet in seminars and conferences to discuss the progress in the field, Indian researchers trying to build the scientific landscape in India could only keep up through journals and by interacting with the occasional visiting professor. So it became important to identify research problems that would have a great impact. This could be seen in two contributions by Ramachandran. In the mid-1950s, he saw the potential of a phenomenon called anomalous scattering in X-ray crystallography.
Atoms scatter X-rays in a normal way, whereas when the wavelength of X-rays approaches a particular limit, an atom may scatter it somewhat anomalously.
This was first discovered by Byford, but Ramachandran was one of the first to use it to actually determine the structure of a compound. And so today anomalous scattering is very, very widely used. That's partly the result of work by Wayne Hendrickson and Keith Hodgson and others.
In 1971, during a brief stint at the University of Chicago, G N Ramachandran got the opportunity to work on a technique called projection reconstruction, which is using 2D X-ray images to develop a 3D image. This area would later become very important as medical technology like MRI and CT scans developed. In both these cases, Ramachandran's contributions were perhaps not very significant in the final outcome. However, they display his knack of identifying the areas of research that would go on to become highly relevant. This talent, combined with his scientific genius and unparalleled drive to do research under any conditions, led him to build a research centre of international reputation.
In post-independence India, he demonstrated that the highest level of science could be done, and it could be done in a place with rather limited facilities.
In fact, we had to go to Guindy Engineering College to use IBM 1620 computers. We used to get about 5 minutes, 6 minutes of time every day.
Ramachandran and team did not complain that they don't have computers to do it, they don't have facilities, they don't have money, and they don't have model kits to do all this. They just wanted to do it.
Ramachandran, by creating the Department of Biophysics and Crystallography, created his own environment.
Professor Ramachandran, of course, was a very towering researcher.
And he attracted the brilliant students to the department. It was only his personality that he could attract all the brilliant students.
It did an upwelling of the science in the campus.
I mean, he did all this work when he was in his 30s and 40s.
For a while, it was really on the map in the world. People, very famous people, Linus Pauling or Dorothy Hodgkin, they would come there for conferences.
Generally, it was conducted abroad. But he used to attract the scientists to Madras University, and we'll have a grand meeting of several Nobel laureates.
Imagine Nobel Prize winners being brought to Chennai city, all in one day in one platform, and the kind of influence it produced on the teenagers.
The research environment is quite important. It means that you have colleagues who are doing excellent work.
Professor Pauling came as a Sir C. V. Raman chair of the Madras University. This professorship was created by Professor Ramachandran in the University of Madras in honor of his guru.
Pauling, during the presidential address at the 1967 symposium, publicly congratulated Ramachandran for solving the structure of collagen. The recognition received by the department also helped them improve their infrastructure.
He had one of the first computers in India.
Professor Bragg wrote a recommendation letter to Government of India, suggesting that the Professor Ramachandran has been doing phenomenal work and he deserves a computer. But subsequently he got this computer as a gift from UNESCO fact, we were quite excited about having a computer and we could do lots of computation.
These earned him a number of accolades, including the Ewald Prize, the top prize in crystallography, and the Fellowship of the Royal Society.
I mean, for me, the great surprise was that he never got the Nobel Prize. And I think that what Ramachandran did for our subject was as innovative as many of the innovations that, in fact, resulted in Nobel Prizes.
And not getting the Nobel Prize is a lottery game. It's not something worth losing sleep on. But did it affect him? He never said so. It's there in the textbooks. So I think that's good enough.
The Ramachandran map was there since I can remember anything about proteins.
And you know, there is no biochemistry textbook that doesn't have very close to the beginning a Ramachandran map.
Ramachandran's successes would not be possible without the complete administrative support under A.L. Mudaliar, and he certainly held up his end in making his department a center of world-class research.
And very often I've heard this term being used that Professor GNR was like a son to Dr. A.L. Mudaliar.
When Mudaliar's term ended in 1969, Ramachandran decided to return to his alma mater. Under the support of the director of the Indian Institute of Science, Satish Dhawan, Ramachandran founded the Molecular Biophysics Unit in 1971. He recreated an environment of excellence, as graduates of this department can be found in almost all structural biology departments in India.
The way his mind worked, I think he also wanted to always take up new things. So he got interested in what is called mathematical logic and things like that.
When we were students in IISER, Professor Ramachandran was there working on mathematical logic. He used to work in a room in the library, and we used to watch him every day as a mystical figure. He used to come very early in the morning, go very late in the evening, just working alone like a saint. He doesn't interact with anybody in the system. I think he was deeply trying to develop the mathematical logic, and for us, he was an inspiration from a distance.
And it also demonstrates the kind of commitment that he had to his science. He had that right to the end.
Even at that age, I think he was 75 maybe, he could think of new ideas, discuss it very well.
It would have been 91 or so. He came and visited me. He was busy going and meeting a professor in the US to convince him that a particular piece of work he had done was actually very significant for biophysics and all that. So I mean, he was a driven person even then.
Indian science lost a great warrior in April 2001. But along with his remarkable contributions to science, Ramachandran also has one of the greatest stories in Indian science. The story of a man primed for scientific greatness, who would not only overcome many adversities, but turn some of them into his greatest achievements.
Those were exciting days, you know. When Ramachandran was a student there in the Indian Institute of Science, and we used to play in the college hostel there. You know. And I got into trouble at one time because the warden said, don't play here because you're probably breaking the tiles here, so you shouldn't play anymore. And he issued a warning. If you continue to play, I will have you dismissed from hotel. But we were young and we didn't care too much for this warden who gave that washing. And myself and Ramseshan were served notice by the hostel warden. And we had to appear before the director and all that. And Director Kannadi Iyer was a very wonderful man. He said, you young people, you don't live by the law and what not, he said something. And we simply say, you must at least say, I'm sorry for what you did. And then he winked at us and then he did like that. He wanted us to say sorry because of the warden. He wanted to please the warden. But then he really didn't want us to express it. He was very happy that we did what we did. And then towards the end, Don't tell anybody I winked at you.